fill in for everybody. It's never accurate. So like every seminar class, I see people's chins. Yeah. And I'm like,
That's not you.
I don't think that's right. It's not made up for.
Photoshop.
Yeah.
Yeah, no, I definitely.
Dr. Nugget,
Yep.
keeps telling me I accidentally uploaded this without knitting. So I know. Sorry.
Problematic.
Yeah. You can just ignore that first one. But the second one that I'm trying to send after knitting keeps telling me that the Word template document does not exist.
Is it in the same folder as your RMD file?
Yes.
Is it named the same, or if you downloaded it, did it add like a number to it?
Good question. I haven't saved here. Oh,
yeah,
one.
It is.
Take down one.
Yeah, take off that parentheses and one.
That should be it then.
Hopefully.
Alright.
I was so happy when you said that. I was laughing so hard.
All right. So, homework 3. Due today, I think.
Yep.
Right? So, if you have issues with the knitting, it doesn't knit. One of the most common causes is due to that Word template file not being in the same folder as that RMD file. Now, if you try to download it again, your browser will probably add a number to that file name. So even though you saved it to that folder, it's not the actual name that's listed in our RMD file. So you have to go back to that folder and make sure that it actually says Word template docx. Make sure that that is true. We're going to have that for our exam. All right. So we have more people here. Don't know why we don't have a huge crowd here. I mean, Friday biostats. This is like we should be selling out.
This is dream.
But there is an ecology exam too.
There it is.
I know there are a couple here that are in both. So, all right, here's our game plan. So we have the exam on Monday. All right, the exam is in 2 parts. All right, Lily, they want to test the online format. Cool. All right, so the exam's in 2 parts. I have it set up as as a theoretical portion that's going to test your basic knowledge. If we were in person and taking a paper test, this would be like equivalent to the closed book part, where I'll ask you definitions, I'll ask you rounding, implied limits, compare contrast terms. As we move forward with this probability, I'll ask you to calculate probabilities, calculate situations with probabilities, because we will do those by hand. As we get to the test, I'll ask you what are the assumptions of a test, what method can we use to check assumptions of the test and so forth. All of those things are what I consider essential knowledge that you should just kind of know offhand. When you read it, you shouldn't have to go look up what the assumptions of the test are. You should just kind of know them. So that, because all of our tests basically have the same assumptions. All right. So that is part 1. Part 2 is the application portion. So exam 1 application. This is an RMD file that you open up just like exam 3. Sorry, not exam 3. Homework 3 and homework 2 and homework 1. All right. So with that RMD file, it'll direct you to do tasks. Create vectors, calculate means, medians, and so forth. All right, I give you the chunks where you write the code in there, and then when you knit the document, it'll execute the code and give, the answers, which I'll be able to see and know that you did it correctly. All right. The RMD file should probably only take you maybe 30 minutes to an hour, possibly. All right, depends on how comfortable you are. Remember that Word that word template docx file, it's going to be the exact same file that I've posted numerous times. It only needs to be in the same folder as the exam RMD file. All right. So if you already have it on the computer, you can copy that file into the different folders, and that could avoid the numbering of the file names that when you would download it. All right. So you could do it that way. The theoretical portion is set up as a Blackboard quiz, Blackboard test. Right? So it's like our previous two, but there's a catch. There's a catch. And I want to kind of warn you about it ahead of time. It's 36 questions. That's how many questions there are. You have 60 minutes to complete it. Right? When you start the test, your 60 minutes starts at that point. Right? So as soon as you click begin, that's your 60 limit time. 60 minutes should be more than enough time. Right? Here's the catch. I have it set up so you get one question at a time. You see one question, answer it, hit the next button or the submit button, and then go to the next one. And you can't go back to any of the previous questions. All right? The 60 minutes, really, this should probably only take you 45 minutes at most. I gave you the extra 15 to account for page loading times and to let you double check some of your answers. So like I do ask you, round a number to a specific place, right? Or give the implied limits. I want you to be able to double check those answers. Like type in the answer and double check it to make sure it's correct before you hit submit. All right? So I think that's going to be a little bit better than requiring you to download like the Respondus monitor stuff and have a webcam handy and kind of show the webcam and everything. I think this will be a suitable approach. All right. So I didn't want to shock you when you sit down and say, "Oh crap, it's one at a time." I'm telling you, it's one at a time. There's only 36 questions, right? And that includes, I don't know, 4 or 5 rounding questions. Right? So it's not like one question you have to round 5 different numbers. It's one at a time. Right? Those exams go live at 5 o'clock in the morning on Monday. All right? They are due by 11:30 at night. All right? We won't have class or lab on that day. So what we'll do is I'll come here at our 11 o'clock time. Make sure it's 11. I'll come here at our 11 o'clock time. So if you wanted to come in here at that time and do the closed book portion, you could. All right. You've got 60-minute time limit to do it. All right. So I would probably get in here and start it a little before 11 because I think there is a class after us. But I'll come in here so that if you have questions, I can answer them. If no one's in here, then I'll stay in here for about 5 minutes or so. If no one comes in, I'm just going to head back to my office. For lab, same thing. I'll come down here, and if people are working in the lab on let's say the application portion, the RMD file, I'll stay here and stick around. So if you get errors, I can help you out, especially with knitting. But I'm not going to lecture on any new material on that day, so that way we can go ahead and take the test. All right. So we won't do new material on Monday. It's just that's going to be the day where we can take our exam. Questions? It's very different, I will tell you. Very different experience. All right. We good? All right, let's talk about probabilities. So we introduced this concept of random sampling. All right. Random samples have equal frequencies to that of the population. So all of our groups, if we're 60-40 in our population, then our sample should be 60-40. That could be 60 males to 40 females. That could be 60% infected, 40% uninfected, and so forth. Now, all those random samples, these frequencies could correspond to probabilities. So in order to kind of understand where we get our p-values from, which is a probability, we have to talk about how to calculate probabilities. We can say that, yeah, this is a math class, we don't need to know it, but as we get further into the course, you will see we will use some of these laws of probability to calculate expected numbers. And then we needed those expected numbers to do, say, a chi-square goodness of fit test and so forth. All right, so in probability, we have the addition rule. The addition rule states that if two events, A and B, are mutually exclusive, then the probability of A or B occurring is equal to the sum of their individual probabilities. All right, so let that thing sink in. If two events, A and B, are mutually exclusive, then the probability that A or B occurs is equal to the sum of their individual probabilities. All right, so mathematically, we write it out as this. P of A or B is equal to the probability of A plus the probability of B. All right, a requirement is that our event, A and B, has to be mutually exclusive. And what does that mean? It means that our events cannot occur together. All right? It's kind of like Schrodinger's cat. Have you heard that one before? What is it?
Poison oxygen. Alive and dead at the same time, right?
Yeah, so you put a cat in a box, right? Poison in there, cat's alive and dead at the same time, all right? Is that a mutually exclusive event, alive and dead? Well, that's what Schrodinger was trying to come up with, all right? More realistic example is flipping a coin, all right? Our outcome is heads or tails, all right? You can't flip a coin and get both heads and tails at the same time because heads and tails are mutually exclusive, all right? So mutually exclusive means our events cannot occur together. And if we ask, what's the probability of getting one or a different event, and these events are mutually exclusive, then that probability is equal to the sum of the individual probabilities occurring. All right, so an example, I've got two examples here. First example is just a six-sided die, single die roll. All right, and I ask you, what's the probability of rolling a 3 or higher number? So that is the probability of rolling a 3 or 4 or 5 or 6. Right? So first up, are the numbers mutually exclusive, or are the outcomes mutually exclusive? Yeah, they are. We can't roll a die and get both a 3 and a 4 appear on the same die. It's just not possible. All right, it's only going to be one number with the roll. So since they're mutually exclusive, we find this probability by adding up the individual probabilities. Well, what is the individual probabilities? Six-sided die. Our item of interest is only one outcome, so probability of rolling a 3, there's only one way to do that, and there's 6 total outcomes, so the probability of rolling a 3 is 1 out of 6, or 1/6. And that's going to be the same for each of these. So 1/6 plus 1/6 plus 1/6 plus 1/6 equals 4/6, or 2/3. So we have a 2/3 chance of rolling a 3 or higher. If we have six-sided die, 2 of them, and we roll 2 of them, kind of like in craps. All right, your first roll at the craps table, if you roll a 7 or an 11, you win. All right, you win your money if you bet on, is it the pass line? I think. So, there's certain bet. There's a lot of different bets you can make, but I think it's the pass line. If you roll on your very first roll, if you roll a 7 or an 11, you win. All right, so the question is, what's the probability that you would win? Well, it's going to be the probability that we roll a 7 or an 11. Go back to Wednesday's class, we said the probability of rolling 7 was 1 out of 6. All right. What about the probability of rolling an 11? What do you think? There's only 2 ways to roll it.
Yeah.
Right?
5 and 6 and a 6 and a 5.
Yeah, 5 and a 6 and a 6 and a 5. Right. Which is 2 out of 36 or 1 out of 18, right? So 1 out of 18 is the 11. 1 out of 6 is the probability of 7. Add those together and we get 2 9s. 2 out of 9 times. How does a casino win? Why do they offer this game?
The odds do their cover.
What's that?
The odds are in their favor.
That's kind of how we always say it, is that the odds are always in their favor. But is it the odds? Or is it the payouts? Right? We're going to win 2 out of 9 times, right? So the odds should be 7 to 2. 7 times we lose, 2 times we win. All right, so we should be paid out 7 bets for every 2 bets that we make, just in order to break even. The casino doesn't pay out that amount. So it's always going to be a losing proposition. You can never get to 0. You can get lucky and be on the good side of things, but that's how casinos work. They don't pay you what the odds should say to pay you. It's a non-zero sum game for casinos. All right, so addition rule. Probability is we just add those together. All right, so mutually exclusive events, these are those that cannot occur together. I have examples here. So flipping a coin, we already talked about. Drawing a card. So if we have a 52 card deck and we take 1 card out and we ask what's the probability of drawing a king or a queen, well, those are mutually exclusive events. We can't draw both a king and a queen at the same time because we're only drawing 1 card. Sex of our offspring, male or female, right? We can't have both. Clutch size, 3 versus 5, right? You can't have both 3 children and 5 children. It's just, can't have it. Can't have it, right? And infection status, you can't be both infected and uninfected, right, at the same time. It's one or the other, right? And I asked the question, can you think of other examples? Yeah, you probably can. Just think about them at your own time. But you have to think, when we calculate probabilities, are the events mutually exclusive? What happens if they're not? All right, occasionally we have events that are not mutually exclusive, which means the events can happen together. All right, this can be 2 different items, so drawing 2 cards out of the deck, now we can get both a king and a queen occurring, all right, because we have 2 cards. This is a situation where we're not mutually exclusive at that point. So mutual exclusion can refer to the 2 different items or characteristics, but it can also be sequences of events as well. So sometimes the sequence of events, we would have said that it can't occur and not occur at the same time, but sometimes they can, depending on what we're measuring and what we're looking at. So examples, sex and hair color. Classic example, and we'll use it for calculating probabilities. All right, so sex, male, female, is mutually exclusive. The hair color, blonde versus brown, is mutually exclusive, but the 2 together are not. So hair color and sex are not mutually exclusive. Age and infection status, not mutually exclusive. The individual ones are. So age is mutually exclusive. So the categories within age are mutually exclusive. And the categories within infection status are mutually exclusive. But taken together, age and infection status are not. Rolling a paradigm. All right, so the outcome on each dice, is mutually exclusive, but since we're rolling 2, now their outcomes are not mutually exclusive. Sex of offspring in a clutch of 4. Now we have our number of offspring and the order of offspring, right? And those are not mutually exclusive events. All right, so how many offspring, and then the order when we have males and females. So you can have 2 males and 2 females in your clutch of 4. But the order in which they occur sets up the situation where it's not mutually exclusive. Because we can have 2 boys first, we can have a boy, a girl, a boy, and a girl. We can have a boy, girl, girl, boy, or we can have girl, boy, boy, girl, and so forth. So you can see all these different combinations to generate our male and female offspring. And again, I asked, can you think of others? Let you think about those. Does mutually exclusive events and non-mutually exclusive events affect our probabilities? Yeah. This is why we had introduced the addition rule. Probability of an event A or B occurring is equal to the sum of their individual probabilities for mutually exclusive events. But if we have non-mutually exclusive events, then we have to account for the possibility of getting them in a certain order. All right? So in order to get to that, the probability of A or B, which is currently hidden by this screen. So what's the probability of A or B? We are going to now introduce the multiplication rule. So the multiplication rule says that if two events are independent but not mutually exclusive, then the probability that A and B occur together is equal to the product of their individual probabilities. The way you can think about it is anytime we ask the or, we're adding. But if we say the and, then those events have to occur no matter what. And in order for that to happen, we account for the probability that the one occurs first, and then we have to multiply that by the probability that our second event occurs. So the and implies multiplication. Now, we've already talked about mutually exclusive events. Now I introduce independent events. So independent events are the probability that one event does not depend on the outcome of the other event. All right? Rolling two dice together. That second die doesn't care what the first die is, what number is on that first dice. It doesn't care. That's an independent event. Playing roulette in a casino. All right? A lot of people like to think, if the marble, I don't know if it's marble or ivory. If the ball lands on a red, well then obviously it must be a black, coming up next. And no, that's not. Each individual spin on that roulette wheel is independent of all of the other spins that happened before it. All right? So, if our events are independent, and if they are not mutually exclusive, meaning that they can occur together, then the probability that A and B occurred together is equal to the product of their probabilities. I do put in a note that if A and B are mutually exclusive, meaning they can't occur together, then that probability that A and B occurred together is undefined. It's not zero, it's just you can't define it. It's not even possible. All right, so here's our example here's our example. Assume that we're looking at fish. Fish can be infected by parasites can be infected by two different parasites that are out there, parasite A and parasite B. Parasite A has a probability of infection of 75%. Right? So if you take a fish, there's a 75% chance that fish is infected by parasite A. This circle represents all of those fish infected by parasite A. Parasite B occurs in 50% of our population. Right? So if we only look at parasite B, if we took out a fish, we have a 50% chance of finding that parasite in the fish. All right? And this circle would represent those fish infected by parasite B. What we're interested in is the probability of finding both A and B in those fish. So in the Venn diagram, it's this shaded area. All right? It's this area where our fish have both A and B. All of these fish have only A. All of these fish have only B. We're interested in that shaded region. How do we get it? Well, are the events independent? Yep, we'll assume that they are independent. So being infected with one does not increase your chance of being infected with the other. And we know that they're not mutually exclusive because we can be infected with both. So using the multiplication rule, probability of A and B together is equal to 75% times 50%, or converted to fractions, 3/4 times 1/2, which is equal to 3/8. All right? Easy, hopefully. All right, so now let's ask that question. Go back to how we did the addition. What's the probability that our fish is infected with either A or B? All right, how do we do that one? Well, let's just kind of talk through it. In this Venn diagram, what are we looking for? What regions are we looking for to answer this question?
Non-overlapping.
Yeah, the spots not go.
Okay,
Like
so
if we say A or B, that means that if they have both, they're excluded. That's not what we're looking for.
no, if they have both, do they have A or B?
They have A and B.
Yeah, they have A. They had so the or just says it's
Yeah.
either A or you have B. It doesn't really exclude the chance that you have A or and B together. It's just
Okay,
Are
so
you-
they still count.
so another way to write this is what's the probability of A or B in terms of the fish parasite example is what's the probability of being infected?
Yeah, okay.
Yeah, all right. So if I ask what's the probability of being infected, you can have A, or you can have B, or you can have A and B. So what regions are we looking for on this diagram? All of them, right? But, so how would we calculate that then? What's your answer to that question then? Why do we subtract out the middle? Who said that? Fred? Yeah. So okay. So that's what we're looking for. So here's our rules. All right. We're looking at probabilities. All right. Overall probabilities. The sum of all of the probabilities of an event will equal to 1. So we look at all possible outcomes. The sum of those will equal 1. So male versus female. Whatever our probability of being male is, all right, probability female will be such that their probability together will equal 1. A common mistake would be to take the addition rule and say, well, A or B, we'll just take these probabilities and add them together. But what happens then? Well, if we add 0.75 to 0.5, we get 1.25. We violate this rule that says probabilities are going to sum to 1. Something's wrong. And as Francisco said, if we add up that 0.75 and we add up this 0.5, what we've done is counted this area twice. And we don't want to do that. So if we're asking what's the probability of A or B, and the events are independent but not mutually exclusive, then what we do is add up our individual probabilities, but then we have to subtract out one of those overlap regions. All right, we have to subtract out one of those overlap regions. So, going back to our example, we already know what that A and B probability is. Where's my cursor here? We already know that. That is 3/8. So our A or B, the probability of just being infected, is equal to 3/4 plus 1/2 minus a 3/8. And that gives us 7/8. So we have 7 out of 8 chances that our fish will be infected with at least one of those parasites. All right, what happens if we have more than 2 independent events? All right, if they're not mutually exclusive, all right, and we're asking what's the probability that all of them occur together, we just multiply all of the individual probabilities. All right, can we do that? Yeah, let's do the daily pick 3. All right, daily pick 3. We ask what's the probability of drawing a 3, a 3, and a 3. All right. Well, we've got 1 out of 10 chances each time, right? So if we want a 3 out of 3, 3, 3, 3 for our daily pick 3, we need, it's 1/10 times 1/10 times 1/10, which gives us, I need that, 1 out of 1,000. Right? So I said we have 1 out of 1,000, and that's how we did it with the probability. I kind of rationalized it with saying, well, our numbers range from 0, 0, 0 all the way up to 999. So we have 1,000, and we're only looking at one number. That gives us 1,000. But mathematically, doing the products, allows us to arrive at the same answer. Now, note, when we do this, when we say the probability of A, B, and C occurring together, we didn't really account for order. We just looked at the individual probabilities and we multiply them together. But order could matter. Order could matter depending on how we ask the question. All right. So with A, B, and C occurring together, and if these are draws and could occur at any time point, we can have it occur as ABC. We could have it as ACB. We could have it as BAC, as BCA, as CAB, and as CBA. All of these still give us that probability of ABC occurring, or the probability of A and B and C. All right. So if we have a situation where order can become important, we have to account for that. We have to account for duplicates in our probabilities. All right. Questions? All right, I think what we're going to do is just stop here. I have these examples, genetics, monohybrid, and dihybrid crosses. So let me get this example up here real quick. I think all of you have probably seen these Punnett squares and stuff and have completed these Punnett squares. All right. Let's zoom in a little bit. Let us get these examples. So what's a monohybrid cross? The monohybrid cross. I think that's really good. What's that?
Big A, you know, big A, whatever. 4 boxes on the Punnett square. Yeah.
Really dark. I feel like we don't have enough light in here. So yeah, monohybrid cross is a single gene, all right, with 2 alleles, all right. So what we want to do is do this. All right. So our question, what's the probability of getting a big A, little a? All right. That's going to be our monohybrid cross. You can do your Punnett square. You can have the answer. I'll show you how we can apply this to using probability. Our next one is a dihybrid cross. All right. So there's our dihybrid cross. What I want you to do, and this will be for Wednesday, is calculate the probability of getting that genotype. All right. I think we can see it. Yep, there. So you can do the Punnett square. That's fine. Have it mapped out. What I'm going to show you how to do is use just our basic probability rules to come up with the answer. And then I'm going to introduce you to a probability tree. So we know what we're supposed to do. I'm going to show you how I arrive at the same answer using a probability tree, because we'll use our probability tree when we start looking at non-independent events. So when a probability depends on another outcome. All right. So we'll stop there. Call it quits. I don't want to do this now and then have you forget about all of this stuff. So I think when we pick it up on Wednesday, it'll be a pretty good review. All right. All right. So look over your notes. I don't know, I might get asked, like, how should I study for this? I would review the presentations, review the notes, write down definitions, write down terms, review your homework. I posted keys on Blackboard. So under the homeworks, I made a new a new item for the keys, which is my markdown document. So I added some comments to your markdown documents. Definitely, you can kind of ignore some of the comments on the first one because I saw on homework number 2, a lot of those were fixed. A lot of anything was fixed because again, you're learning how to use R and Markdown and stuff. So check it out. Just make sure you know how to do the stuff in R. All right. Have a good weekend.
All right.